Hello everyone, welcome to the August talk in our seminar series, which aims to provide accessible introductions to some of the most significant mathematical theorems of the 21st century. Today's talk will last about 45-50 minutes, followed by time for questions and discussion. Please feel free to type your questions or comments at any time in the meeting chat. It's my great pleasure to introduce our today's speaker, Professor Marc Lackenby. He's a leading mathematician in topology, geometry, and group theory, with major contributions to knot theory and low-dimensional topology. In this talk, he will discuss the elementary transformations that relate different diagrams of the same knot or link, and the question how efficiently one can pass between such diagrams. The talk will highlight his polynomial bounds for simplifying diagrams of the unknot and explain recent work extending these ideas to every fixed link type. So it will also describe the consequences for the computational complexity of recognizing knot and links. So I am now happy to hand over to our speaker.
Great. Well, thank you ever so much. It's a real pleasure, a real honor to be giving this talk. So, as Bogdan said, I'm going to be talking about knots and links, right? So a knot is just a smoothly embedded, simple closed curve in a three-dimensional space. Okay, so you should think about just taking a piece of string and tying it up to form a closed curve. And here are the first three knots, in some sense. Simplest one is the unknot. It's just the knot that is the round circle, and there you have the trefoil and the figure eight. And a link is a union of finitely many of these disjoint simple closed curves. And we think of knots and links as equivalent if you can deform one into the other without the curve passing through itself. So, and typically we represent knots and links by means of a diagram, which is just where you project vertically onto the plane, and you keep track of whenever an arc crosses itself over another one, you keep track of which one is the over and which one is the under arc. So this diagram on the left is the trivial diagram of the unknot, but the unknot emits many different diagrams. You can imagine deforming it in three space and projecting it. So a basic question is, if you're given a knot diagram, can we decide whether or not it's actually the unknot? And it seems like a pretty fundamental and basic question in the subject. And the problem is you can get some pretty nasty, complicated diagrams of the unknot. So this is a diagram of the unknot, it turns out, but I challenge anyone to be able to see that. And the conclusion that you get from these sorts of diagrams is there's probably no simple way of deciding whether or not diagram is the unknot. And by simple, I mean some kind of sequence of simplifications to the diagram that take it to the trivial one. Of course, we don't 100% know that's the case, but that certainly seems to be the case. So this question of whether you can recognize the unknot, and more generally, whether you can decide two knots are equivalent, was actually flagged by Alan Turing in his last published paper called Solvable and Unsolvable Problems. So here's a quote: no systematic method is yet known by which one can tell whether two knots are the same. And here's a picture for excerpt from the paper. You can see at the top a diagram of the trefoil knot. And at the bottom, this is also a trefoil knot, but it's expressed as a concatenation of straight lines. And the idea is that you have then represented it, the knot in some computer-friendly format. You can plug this into a computer and you can say, is this the unknot or not? or you could take two such representations and ask whether these are equivalent knots. And so, although he didn't specifically say this, Turing was clearly raising this as a potentially unsolvable problem. And it's known that there are many simple questions like this that are actually unsolvable that computers can't do. But it turns out that this particular problem is solvable, as we can see, as we will see. So when you're faced with this sort of question, the first thing you should try to ask yourself is there a sequence of simple modifications that one can make to a diagram with the property that any two diagrams of a knot differ by a sequence of these moves? And this was actually, such moves were established by Reidemeister over 100 years ago. They're called Reidemeister moves. Any two diagrams differ by a sequence of these three types of moves that you can see. So this actually has an algorithmic consequence. It means that given a diagram of the unknot, for example, you will always eventually be able to prove that it's the unknot. The reason is that given my unknot diagram, there are only finitely many potential Reidemeister moves. So perform all of those, you get a collection of diagrams. Then perform all possible Reidemeister moves to those, and you get a collection of new diagrams, etc., etc., etc. And by Reidemeister's theorem, you will eventually get to the trivial diagram with no crossings. And so you'll eventually proved that your unknot that you had to begin with really is the unknot. This does not lead to an algorithm, though, because if someone had given you a non-trivial knot and you had applied this procedure, the process would never terminate. So a very natural question is, do you know when to give up? In other words, if you know in advance how many moves are required, you would have an algorithm to decide whether two knots are equivalent. Or if you just knew how many moves you need for the unknot, you would have an algorithm to decide whether a given diagram represents the unknot. So this is actually, you can formalize this as the following easy theorem, that the following are equivalent. There's an algorithm to decide whether a knot diagram represents the unknot. That's equivalent to the existence of a computable function, f, from the natural numbers to the natural numbers, with the property that if you're given a diagram with n crossings, then there's a sequence of at most fn Reidemeister moves, taking it to the trivial diagram. So computable means that a computer can compute it. So I've sort of described one direction of this easy theorem, that if you have a computable function f, you know when to give up. And so the procedure that I just described tells you when to stop if you happen to have a non-trivial knot. But it turns out that the implication goes the other way. So upper bounds on Reidemeister moves are completely related to the algorithmic questions of unknot detection and more generally solving the equivalence problem. Okay, so what was known? Well, an exponential upper bound was proved by Haas and Lagarius in 2001. So they proved that if you're given a diagram of the unknot with n crossings, then you can take it to the trivial diagram using at most 2 to the kn Reidemeister moves, where k is 10 to the 11. So it was a great result, and I will explain shortly, actually, the outline of their proof. What about lower bounds? Well, there's a sort of trivial linear lower bound, that if I have a diagram with n crossings of the unknot, I need at least n over 2 Reidemeister moves to take it to the trivial diagram. And that's just because each Reidemeister move changes the number of crossings by at most 2. In fact, actually, there are examples, there's a theorem due to Haas and Novick, that say that actually you might need quadratically many Reidemeister moves. But so we need at least potentially quadratic, sometimes at most exponential. And the question was asked, where does the truth lie? And in particular, is there a polynomial upper bound? And here's a little quote from Bill Thurston in 2011. A lot of people have thought about this question, but it has been a very hard question to resolve. And that's the theorem that I want to talk about today, that in fact there is a polynomial upper bound on the number of Reidemeister moves that you need. Given a diagram of the unknot with n crossings, you can transform it to the trivial diagram using at most 236n all to the power 11 Reidemeister moves. So that's actually quite a big number, but it's a polynomial, and that's what the problem was about. Okay, so I'm going to give some of the background to this theorem, and really the theorem builds on work of several people. So I'm mostly going to focus on their work rather than mine, and just at the end I'll bring it all together. So really the story starts with the work of Harkin, as we'll see. But what you obviously need to do is somehow you need some kind of topological characterization of the unknot, right? You've got to know, you're given a knot, you've got to somehow use the fact that it's the unknot. And here's a topological characterization. So the round circle obviously bounds a disk. And more generally, a knot is the unknot if and only if it bounds a smoothly embedded disk in three-dimensional space. Okay, so the proof of this is as follows. Suppose I start off with a round unknot and I deform it to some other representative of this unknot. Well, as I deform this, I can deform the disk that it bounds with it. So it doesn't stay flat, but it still stays as a smoothly embedded disk. And so that shows you that the unknot always bounds a smoothly embedded disk. Conversely, if you bound a smoothly embedded disk, you can slide the knot over that disk until it becomes a little almost round circle, and hence you had the unknot. Okay, so that's a characterization of being an unknot. And this disk is called a spanning disk and is obviously going to play a major role. Another thing that we do is we work with the knot exterior. So this is a topological space. The first thing we do is, instead of viewing the knot as living inside R3, it's more convenient to think of it as living inside the three sphere, S3. So S3 is the one-point compactification of R3. You just add an extra point at infinity. And the other thing that we do is we drill out the knot. So you drill out the knot and remove an open regular neighborhood of the knot from the three sphere. And the reason for that is that what's left is a compact three manifold with toral boundary. So if you're not familiar with manifolds, or specifically three manifolds, don't worry too much. I'm not going to be using too much manifold theory in this talk. Okay, so as I mentioned, the unknot recognition problem is solved. It was solved by Wolfgang Harkin in the early 1960s. There is an algorithm to determine whether a knot diagram represents the unknot. So Harkin is probably more famous for proving the four-color theorem with Appel. But before he looked at the four-color theorem, he had proved some very important theorems about knots and links and about three manifolds. Okay, so I want to explain Harkin's theorem. And it uses what's called normal surfaces. So we're working with the exterior of a knot. It's a three-manifold with boundary. And what we do is we triangulate it. So a triangulation of a three-manifold is a way of writing the three-manifold, expressing the three-manifold as a collection of tetrahedra with their faces glued in pairs. Okay, so it's actually pretty straightforward from a given diagram of a knot, say n crossings, to build a triangulation of its exterior just using linearly many tetrahedra. Okay, and now we're assuming that the knot is the unknot. Well, in this theorem, there's an algorithm to decide whether it's the unknot, but let's just for the moment assume that we have the unknot. Then we know that we have a spanning disk. And this sits inside the three-manifold as a surface. And what Harkin realized is that you can put that surface into normal form. And that means it intersects each tetrahedron in a collection of triangles, as shown, squares. Now, in fact, normal surfaces had been studied before by Kneser in the 1930s, but Harkin really pushed the theory forward. And one of his observations was that we should really just encode the normal surface by a list of non-negative integers. You see, going backwards, I've drawn a triangle and a tetrahedron here, but in a normal surface, you're allowed to have many parallel copies of that triangle. And so what you just do is you just count the number of triangles and squares of each type. So in each tetrahedron, there are 7 different triangles and squares. And so if you have T tetrahedra, you have a list of 7 T numbers. And that's called the vector of the surface. And they satisfy various conditions, one of which is called the matching equations. So if I have a face of my triangulation with tetrahedra on each side, then when I have a normal surface, it has to patch together correctly along the face. So in this particular case here, if I have, say, x1 copies of the triangle on the left and x2 copies of the square, and similarly x3 and x4 on the right-hand side, then x1 plus x2 has to equal x3 plus x4 in order for the surface to patch together. So there are these equations. There are 3 equations for each face, and they're called the matching equations. There are some extra conditions called the compatibility conditions, which say that, in fact, you cannot have 2 different square types within the same tetrahedron. So just going backwards, there are 3 different types of square in each tetrahedron, but if 2 coexist, then they have to intersect each other. And so my surface, my spanning disk, wouldn't then be embedded. And we're only thinking about embedded surfaces. So compatibility condition says that that doesn't happen. And then Harkin proved that there's a 1-1 correspondence between properly embedded normal surfaces up to some suitable equivalence relation and non-negative integer solutions to the matching equations, satisfying the compatibility conditions. So in some sense, what you've done is you've changed your study of normal surfaces to almost linear algebra. And from a topological point of view, this does not seem like a good idea, but in fact, it is. So because you can use tools from linear algebra, and in particular, you can introduce this definition. We say that a normal surface S is a sum of 2 other normal surfaces, S1 and S2, if their vectors add as shown. So that's a linear algebraic condition. It's not clear what's going on topologically, how the surfaces S, S1 and S2 are all related to each other, but that's how they're encoded. That's how they're related via the algebra. And then we introduce the definition, say that a surface is fundamental if it cannot be written as a non-trivial sum. Okay, So these are all definitions due to Harkin. And then Harkin proves some facts. Suppose that I have the exterior of the unknot triangulated in some way. Well, because we have the unknot, we know that it has a spanning disk. But Harkin proved, in fact, more that you can put the spanning disk in normal form. And furthermore, you can actually make it fundamental. Secondly, there's an algorithm to construct all fundamental normal surfaces. This turns out to be just fairly basic linear algebra. The first part is non-trivial topology. The second part is fairly basic linear algebra. So here's Harkin's algorithm. You're given a diagram of a knot. Use that to construct a triangulation of the knot exterior. Then, using the second of these theorems, enumerate all fundamental normal surfaces in that triangulation. There are only finitely many. Go through them each one at a time and say, is it a spanning disk? So given a surface like that, you can easily check whether it's a spanning disk. And if one is a spanning disk, then we know we have the unknot. If none are, then we know we have a non-trivial knot. So that's Harkin's algorithm. It's still extremely important. And Haas and Lagerius gave their exponential upper bound on Reidemeister moves using this. So now what I want to do is I want to explain the proof of their theorem. So now I'm given a diagram of the unknot with n crossings, and I want to give you a sequence of Reidemeister moves, taking that unknot diagram to the trivial one. So this relies on an observation of Haas and Lagerius that fundamental normal surfaces aren't too big. Again, this is fairly basic linear algebra. That if I have a triangulation with T tetrahedra, then any fundamental normal surface has at most exponentially many squares and triangles. Okay, so in particular, my spanning disk has a normal representative with at most that many squares and triangles. So how does that argument go? Again, we build a triangulation of the knot exterior. Again, find a spanning disk which is normal and fundamental. So it's not too big. And now just slide the knot over the disk. And as you slide the knot over the disk, look at the projection of the knot. As you deform the knot, as you slide it over the disk, the projection changes. You slide it across the triangle, one triangle or square at each time. You can estimate how many Reidemeister moves these diagrams gradually change, and they gradually change using Reidemeister moves, and you can estimate how many you need as you go across each triangle or square. Because we had only exponentially many triangles and squares, you therefore need only exponentially many Reidemeister moves. Okay, so that's the proof of their theorem. And you can say, well, how are we going to improve that? How are we going to get to a polynomial bound? Well, there's an obvious strategy, which is to say, did we really need exponentially many triangles and squares? Might there be a spanning disk with only polynomially many squares and triangles? Unfortunately, the answer to that question is no. In general, you may need exponentially many triangles and squares. And there are some examples due to Haas, Snowink, and Thurston. So what they did is for each natural number n, they created a representative of the unknot as a concatenation of 10n plus 9 straight arcs, so linear in n. Because they're unknots, they bound piecewise linear spanning disks. But they proved that for any such disk, it has to have exponentially many triangular faces. The construction is sort of explained in outline here. You can see on the left a little unknot, and then here you modify that unknot by inserting a closed braid followed by its inverse. So topologically that doesn't change anything, but this region in the middle gets highly twisted up, and you can see how a disk has to intersect that region, and it has to be exponentially big. Okay, so this unfortunately means that you cannot beat having exponentially large spanning disks, and that means another idea is needed. So at this point, I go to a completely different method of detecting the unknot, using work of Ivan Dynakov, which was completely groundbreaking. And this is, in some sense, when the first time you see it, it's very strange. So he worked with rectangular diagrams. So a diagram is rectangular if it's a union of horizontal and vertical arcs, as you can see here. Vertical, horizontal, etc. Subject to the following condition, that whenever two such things cross in the plane, that means a vertical arc is going over a horizontal arc, the vertical arc is always the over arc. Now, this is a really strange condition. It's not at all clear why this is a useful thing to do, but it turns out it really is. So because we're going vertical, horizontal, an equal number of vertical and horizontal arcs, and that number is called the arc index of the diagram. So it turns out that given any knot diagram, you can always isotope it and deform it a bit to make it rectangular. Okay, so you may as well work with rectangular diagrams. Now, just as for ordinary diagrams, there's a collection of Reidemeister moves which relate any two such diagrams of a knot. So in the setting of rectangular diagrams, there are also a set of moves. Here's one of them. It's called a cyclic permutation. Here what you do is on the left, you look at the leftmost vertical arc. And you pick it up and you move it to the rightmost. That doesn't change the knot type, and it also doesn't change the arc index. Here's another move. In fact, two types of moves, stabilization and destabilization. So stabilization just adds on a little loop or a little kink to your rectangular diagram. It just increases the arc index by 1. Destabilization is the reverse of that. So these moves look pretty benign, but it turns out that stabilization really is our enemy. And the reason is it increases the arc index. So if you stabilize lots and lots of times without bound, you're dealing with diagrams that become arbitrarily complicated. And then there's a third type of move called an exchange move. What happens here is, suppose I have two horizontal arcs of my diagram that are adjacent in the sense that they have like adjacent heights. And suppose that they don't interleave like my arms are doing, that their projections onto the x-axis are either disjoint or one is completely contained within the other. Then you can interchange their heights without changing the knot type. And that's called an exchange move. And that also doesn't change the arc index. Okay, so it's a theorem of Cromwell that any two diagrams, rectangular diagrams of a knot or link, differ by a sequence of these moves. But Dynakov, in the case of the unknot, proved something very striking indeed. He proved that any rectangular diagram of the unknot can be reduced to the trivial diagram, which is just a little square in the plane, using cyclic permutations, exchange moves, and destabilizations. In other words, stabilizations are never required. And so this, by the way, is in contrast to the situation with Reidemeister moves. In the case of Reidemeister moves, there are lots of diagrams of the unknot, where any sequence of Reidemeister moves, taking it to the trivial diagram, has to increase the crossing number. However, in the case of rectangular diagrams, the natural measure is the arc index, and this shows you never need to increase the arc index. This theorem also gives you a completely different unknot recognition algorithm, because what you can do is someone gives you a diagram, a rectangular diagram, and says, is this the unknot? Well, you can just start applying all possible cyclic permutations, all possible exchange moves, and if you see a destabilization, perform that. And the point is that because you're staying in the realm of bounded arc index, this search space that you're exploring is finite. And so at some point you will have explored everything, and you'll have either have got down to the trivial rectangular diagram, or you will have not, and you will know that there is no way of getting to the trivial rectangular diagram from your given one using these moves, and so you will know that it's not the unknot. It also has one other really excellent consequence, which is that instead of considering how many Reidemeister moves you need, you can ask how many crossings do the intermediate diagrams have? And Dinokhov proved that if you start off with the diagram of the unknot with n crossings, then in fact there's a sequence of Reidemeister moves that takes it to the trivial diagram and only goes via diagrams where the number of crossings is at most 2 times n plus 1 squared. So how does the proof go? Well, you take your diagram of the unknot with n crossings, you make it rectangular. Let's say it still has arc index n. Then, well, now I stay in the world of diagrams with arc index n. I have at most n vertical arcs, n horizontal arcs. When you project them, they can have at most n squared crossings. And so you stay in the world of quadratically many crossings. Okay, so in the next few minutes, I want to try to give some ideas behind Dinokhov's proof. It's kind of remarkable. And I now need to make another leap in another direction in order to explain Dinokhov's argument. So this is yet another way of representing knots and links, called arc presentations. And at first sight, it seems to have nothing to do with what I've just been talking about, so just bear with me. So in this setup, you fix a round circle in 3-dimensional space called the binding circle. So it bounds a disk, but actually it bounds many disks. I could take that disk and push it up a bit. Bounds a 1-parameter family of disks. I could take that disk and push it down a bit. And in fact, I can fill up all of the 3-sphere with such disks. Those disks are called pages, and this is what's called an open book decomposition of the 3-sphere. So on the right-hand side here, you can see sort of an excerpt of this open book decomposition. So in the center, there's a subset of the binding circle. And coming out of it, you can see this 1-parameter family of bits of disk, the pages. And so you can see, because of the picture on the right-hand side, why it's called an open book decomposition. There's like the leaves of a book all bound together along the binding circle. Okay, so you just fix that at the outset. And then you say that a link L is in what's called an arc presentation. if the following holds. It intersects the binding circle in finitely many points. So here you can see a knot, in fact the unknot, in an arc presentation, and you can see that it intersects the binding circle at 3 points. And between these points there are arcs of the knot, and each one is required to lie inside a page. And in fact, in each page there's either one arc or nothing. Okay, so here you can see the knot is going sort of from one point on the binding circle to the other through a page above the horizontal plane, then it goes in a page below the horizontal plane, and then it kind of goes in the horizontal plane. Okay, so it turns out that any link can be put in an arc presentation, but more striking is the following, that there's a 1-1 correspondence between arc presentations and rectangular diagrams up to cyclic permutation. So this may be best described by means of an example. So this example that I was showing here, this is an arc presentation of the unknot consisting of a concatenation of 3 arcs. Each of those arcs lies in a page, so you can think of those as having 3 different heights. Those are going to be our 3 different vertical coordinates in the rectangular diagram on the right-hand side. Also, there are these 3 points on the binding circle. They're parameterized by an angle between 0 and 2 pi. You just put your 3 vertical arcs, you give them their x coordinate as being those 3 angles. So the fact that this unknot on the left intersects the binding circle at 3 points means we convert to a rectangular diagram with arc index 3. Okay, so it's not obvious from what I've just described that this really is the same link type, but in fact it is. The main message to this is that these 2 seemingly very different ways of representing a knot, one via rectangular diagrams, the other via arc presentations, are actually equivalent. So really, mostly Dinokhov works with arc presentations rather than rectangular diagrams. And the reason is that suppose I have the unknot. Well, we know that it has a spanning disk. That spanning disk then inherits a singular foliation. Okay, so let me explain how that works. So just going backwards, we have our knot there on the left-hand side bounding a disk. Now, in general, that disk might slice through the binding circle transversely. And we know that coming out of that binding circle, there is all these pages. If I look at the intersection between my spanning disk and these pages, I get a picture like the left-hand side here, like A. You have a singularity where the spanning disk slices through the binding circle, and the pages coming out of it give you these leaves of this foliation. You might have other singularities. For example, you might have C here. So there are 5 types of singularity that you can have, but let's just focus on C at the moment. So let's just throw away the right-hand 2 and then look at C. So this arises as follows. This arises away from the binding circle. So away from the binding circle, we have this 1 parameter family of pages. You can think of those as parameterized by a height function. And my surface S, my spanning disk S, might look like this with respect to the height function. It might look sort of saddle-shaped at some point. This is called a Morse singularity. And then you can see here the intersection with the pages. And what you get is, you get this sort of singularity in the middle, which is exactly where the disk has this saddle, where you have these 2 arcs, that sort of, or 4 arcs coming out of this point. So you can think of these as sort of contour lines in a kind of like a map on the circle, where the contour lines are showing the intersection with any given page. So it's fairly standard bit of topology that you can always make your surface have these so-called Morse singularities, and this one C is the saddle. The one B here is where you have a little local maximum. You have some point of your spanning disk just touching a page, and everything else is below that. Okay, so what this does then is this actually specifies a graph lying inside my spanning disk. You have these vertices, two types of vertex, or three types of vertex, A, B, and C. A is where the spanning disk slices through the binding circle. C is where the saddles are. Don't worry so much about B, you can ignore those. And crucially then, so those are going to be the vertices of my graph. You also have these edges, which are called separatrices. These are the things coming, the four singular leaves coming out of the saddle. They have to end somewhere, and typically they'll end on one of the A vertices. So those are called separatrices. So whenever you have this graph sitting inside your spanning disk. And there's various, I'll give bits of terminology, which I'll explain in just a bit, but the crucial thing is that in any planar graph, if it's a simple graph, then in any planar graph, there's always a vertex of degree at most 5. This is a famous Euler characteristic argument, using essentially the fact that the Euler characteristic of the disk is positive. In our setting, this graph that we create has more structure, and in fact, it always has to be not a vertex of degree at most 5, but in fact, either a pole, like the singularity we saw in B before, or a 2-valent vertex in the interior of the disk, or a 3-valent vertex in the interior of the disk, or a 1-valent vertex on the boundary. So those are the number of separatrices coming out of it. Bit of terminology, valency is the number of separatrices coming out of a vertex, and the star of the vertex is all of the union of the leaves emanating from it. So what Denikov says is that we always have in our spanning disk some low valency vertex. And then he says in each case, there's then a modification that we can make to the arc presentation, which reduces the number of singularities of the disk. So you keep on going. Each one of these modifications is used as a sequence of exchange moves, cyclic permutations, maybe a destabilization. And each stage you simplify your disk until you get down to a disk with as few singularities as possible. And that means that your arc presentation has actually been simplified down to nothing, down to just the trivial one. So that's the overview of Denikov's argument. It's highly non-obvious. In summary, let me just summarize it again. I've got an arc presentation of the unknot. It bounds a spanning disk. That disk then inherits a singular foliation coming from the intersection with the binding circle and the pages. That really gives you the separatrices that give you a planar graph. There's always a vertex in there of low valency. When you have such a vertex, there's a move that you can do to simplify your disk. Let me explain some of these moves. So this is an example of the singular foliation near the boundary of the disk. And this is a 1-valent boundary vertex. So S here has just a single separatrix coming out of it. This is what it looks like in the arc presentation. You have, so running horizontally along the top figure, there's the knot. It has these vertices S1, S, S2. That's, you can see in the lower bit, you have your knot K, and it's going from S1 to S to S2. And there's a bit of the disk, an incident to it. And then there's a move that you can do which reduces the number of vertices of the knot. That produces the arc index of the knot, and that's actually a destabilization. If you have a two-valent interior vertex, this is what it looks like inside the disk. This is the disk in three-dimensional space. And you can see it sort of wiggles through like so. Kind of schematically, it looks like what's going on the left here. There's my spanning disk S, and here it's intersecting the binding circle in 3 points. And the move that you make moves the spanning disk. It reduces the number of intersections with the binding circle, and we've simplified our disk. Okay, so that's Dynikoff's argument. Now, in the last few minutes, I'm just going to explain what I do. I use both these ideas. I blend Dynikoff's methods with the use of normal surfaces. And here's an outline of the proof. You start with a diagram of the unknot K with n crossings. And what we want to do is we want to find polynomially many Reidemeister moves, which takes it to the trivial diagram. First of all, you move it so it's a rectangular diagram, and you don't need to increase the arc index. The arc index is at most 5n. Then you create a triangulation, in this case actually not of the exterior of the knot, but of the whole 3-sphere. And it doesn't have that many tetrahedra, 5n squared. And you arrange that K and the binding circle are both simplicial in this triangulation. Now, using normal surface theory, we know that there's a spanning disk which is at most exponentially large. In fact, in this case, at most this quantity here, 2 to the 10 to the 8 to the n squared. And that's the number of intersections, that's an upper bound for the number of intersections with the binding circle. We know from Dynikoff's work that there's always, because we have a spanning disk, there's always a 3-valent or 2-valent interior vertex or a 1-valent boundary vertex. So this disk inherits this singular foliation. But the key idea is that actually you could find a large collection of these which all have parallel stars. So what do I mean by that? Just going back a bit, let's just look at this modification here to our disk. Here our disk went through the binding circle 3 times. But say I had lots and lots of bits of this disk, all of which ran parallel like so, sort of 1 million of these bits of disk that went through the binding circle near S2, then through the binding circle near S, and then near the binding circle near S1. Then I could do this move and reduce the number of singularities, the number of intersections with the binding circle by a huge amount. So that's actually what you do. You actually reduce not the number of intersections with the binding circle, not by 2, but by a definite factor. And so that means because you had most exponentially complicated spanning disk, the number of moves you need is at most polynomial. So in my slides, I don't have time to describe it, but in my slides, I explain a little bit more about what's going on with parallelism and how normal surfaces allow you to talk about bits of surface running parallel to bits of other surface. But because of lack of time, I'll skip that. This is a sort of a quick summary of the proof. Just briefly want to close by discussing non-trivial knots and links. So you can ask, this theorem was about the unknot. What about non-trivial knots? And here's a theorem which I put on the archive recently. It's an analog of the thing for unknots. It says that for each link type K, so for example, the trefoil or the figure 8, there's a polynomial pk with the following property. That if I have a diagram, 2 diagrams, D1 and D2 for the knot with N1 and N2 crossings, then there's a sequence of Reidemeister moves relating them, which is a most polynomial length, pkn1 plus pkn2. The techniques are similar. It uses many of the same ideas as in the case of the unknot. The thing about a non-trivial knot is there's no analog of a spanning disk. So in fact, what we use is a sequence of surfaces called hierarchies that decompose the exterior of the link into 3 balls. I won't say any more about the method, but I'll just mention that you can compute these polynomials. They're pretty big. Here's the polynomial for the trefoil. It has degree a little bit less than 300,000. Here's the polynomial for the figure 8. It has a degree a bit more than 15 million. So it's amazing. If you say polynomial, it doesn't seem too big, but these are pretty big polynomials. Let me just close by a few unsolved problems. This does not give a polynomial time algorithm to recognize the unknot. It gives a polynomial bound on the number of Reidemeister moves that you need, but it's not clear given a diagram which sequence of moves you should take. And I personally don't think that Reidemeister moves, I could be wrong, but I don't think Reidemeister moves will solve this problem. So this is a famous unsolved problem. Another one, a very interesting one, is there a universal polynomial pk that works for all link types k? In other words, given any 2 diagrams of any knot or link, do they differ by at most pkn1 plus pkn2 Reidemeister moves for some universal polynomial? We don't know this. In fact, the best thing that we know is the following theorem. I'll close with this as a statement of how little we know. That if I don't fix my knot or link type, if I just think about any knot or link k, and I have 2 diagrams of k with n1 and n2 crossings, then this is the best known upper bound on the number of Reidemeister moves you need to relate them. 2 to the 2 to the 2 to the 2 to the tower of 2s with n1 plus n2 at the top. How high is that tower of 2? Its height k to the n1 plus n2, where k is 10 to the power 1 million. So although we know a lot about knots and links, I think you can say here that there's definitely more work to be done. And I'll leave it there. Thank you very much.
Okay, yeah, thank you for your talk. So for everyone, I unmute now. I allow you to unmute yourself. So you can now unmute yourself and ask questions in voice if you like. Or you can type your questions in the chat, and then either me or Professor Marc will read them. Okay. So I see first raise hand. So please just sit hard. Please go ahead.
So I know that the quest to find a polynomial time algorithm for the unknot is quite a major question in topology, but does it have any implications in computational theory per se?
I mean, that's a good question. Not that I'm aware of. I think it plays an interesting, it serves as an interesting example in computational theory. So this problem is in the complexity class NP. In other words, you can certify a yes answer in polynomial time. And in fact, my sequence of Reidemeister moves gives you such a certificate. It's also known to be in complexity class co-NP. In other words, you can certify a no answer in polynomial time. This is using very different methods from what I've described here. And then, so it's almost certainly not, therefore, not NP complete. Any problem that's in NP and co-NP is widely believed not to be NP complete. That would mean that if there was a single problem, that would mean that NP equals co-NP, which everyone thinks isn't the case. So this is a good candidate. It's not, but yet it's not known to be in polynomial time. So this is a good candidate for an intermediate, an NP intermediate problem. And there aren't too many natural problems out there which are believed to be NP intermediate. And so although this doesn't actually have any ramifications for complexity theory per se, this is actually a kind of an interesting example in the world of complexity theory.
Okay, thank you. Can you now open the chat and read question from there, because it's a long question.
Sure. Now, how do I do that? I might stop sharing my screen if that's all right, because I can't see the chat.
That's okay. If somebody will ask, you can share it again.
Oh, we can always share again. Yeah. Let me see. Sorry, you'll just have to bear with me while I find the chat. There we go. Right. Okay, so first question is, do I believe there's a polynomial time algorithm for unknotting? Excellent question. I don't know. I have announced, and I'm currently writing up a quasi-polynomial time algorithm, and I don't know whether you can get as far as polynomial time. I think it's a very interesting question. Is there a polynomial time quantum algorithm? Also an excellent question. I don't know. I don't know. It's not so completely crazy. The world of quantum algorithms has been related to, for example, the Jones polynomial. So it's possible that there might be. I don't know. It's not completely inconceivable. The answer to that is yes, but I don't know. That's
okay.
The only. Yeah.
Thank you for answering. Just one follow-up.
Yeah.
Do you think? Sorry, what does quasi-polynomial?
Quasi-polynomial time.
Log.
Quasi-polynomial time means the following. So it's 2 to the power of log n to some constant power. So, for example, if it was 2 to the power log n, that would be polynomial. This is actually the algorithm I'm writing down is 2 to the power log n to the power 3.
Right.
So it's just a little bit worse than polynomial.
Okay. So in practice, it might be usable.
Okay. So in terms of practical algorithms, so the proof of quasi-polynomial time, as I say, I'm writing up, but the vanilla version of the algorithm is out. I put it out on the archive within the last month. And although it hasn't been implemented, I am very optimistic that it is going to be super practical. And so I actually think, yeah, I think you'd be, I mean, I don't have any real evidence to this other than a pretty strong hunch, but I think that you'll be able to deal with knots with hundreds of crossings and decide whether they're trivial or not. But we shall see whether that actually comes to pass.
Interesting. Thank you very much.
Sure.
Have you tried to ask ChatGPT to implement algorithm?
Well, that would save myself a lot of time. I think the implementation, although I think the algorithm is fast, the implementation could be a bit of a pain in the neck. So, but I do really want to try. Actually, I think it's a really interesting thing to try to do.
Yes, there's one more new question.
Next, from a data science book, could we interpret any real-world planar graph as a morph graph of some disk folio intersection and characterize the graph in some way? Yeah, it's a good question. Like, add a bit of extra structure to your graph, and then you have it as this singular foliation. And then you could then ask, does it embed inside the 3-sphere in a nice way? It's an interesting question. I don't know the answer to it. but I like the question. I don't know the answer. Yeah.
I also wanted to ask, in your Haken algorithm, very first algorithm, it looks like very topological. You have it represented in three-dimensional space. You have complement regulation and everything. So, but if we represent the knot in three space, there is no crossing at all. So how's the number of crossing going to the picture? Or if it's like constant time algorithm, independent
It's because,
of crossing?
no, it's because the key measure is the number of tetrahedra in the triangulation. And given a diagram with n crossings, there's a fairly straightforward algorithm to build a triangulation for its exterior with, say, 8n tetrahedra. So, but really, as far as Harkin's algorithm is concerned, it's really just the number of tetrahedra you need. And this is sort of substitute for the crossing number and is bounded linearly above by the crossing number. But there are actually some knots where you have a triangulation with the number of tetrahedra is much smaller than the crossing number. So that's the key measure.
Yeah, so it's interesting, different input, and if the number of triangulation is much smaller, then the algorithm can be much faster.
Yeah, right. So yeah, I mean, I should say that Harkin's algorithm has been fully implemented in a very nice program called Regina, which was developed by Ben Burton and is now developed and maintained by him and many others. And it's fully implemented, and actually in practice it worked pretty well.
Okay, any other questions?
Do I know of any other real-world implications for the unknot question? Not really. I think it's, yeah, not really. I think it's cool. I think it's nice. It's clearly knots and links. They're clearly real objects, and it's nice to be able to answer questions about them. But if we did have a polynomial diagram algorithm with this, could this be used for other things beyond knot theory? Not as far as I'm aware.
Okay, yes, thank you again very much for talk. So thank you everyone for coming. So if you miss part of the talk, the recording will be available in the YouTube. And welcome for the next seminar. The seminars is once a month, so the next seminar will be in September. Go to the seminar webpage and have a look. Thank you.
Great, thank you very much. Bye.
Thank you very much.